everyone, today we are going to be implementing the famous Q-learning algorithm. Now you've probably heard of deep Q-learning before, and Q-learning is a heavy prerequisite for that, so we're going to get to deep Q-learning in the future. But for today, we're going to be implementing the standard Q-learning algorithm and just explore exactly what makes it different from some of the stuff that we've looked at so far. So Q-learning is another form of temporal difference learning. And so let's just do a really quick recap of last time. I hope you watched the SARSA video because SARSA is a type of temporal difference learning. And temporal difference learning is created to solve some limitations of Monte-Carlo. In Monte-Carlo methods, if you remember from one of our previous videos where we implemented this, in Monte-Carlo methods, we need a trajectory of data. Basically, let's say you have some game, you're going to be playing the game, and as you're playing the game, you're going to be collecting what state was I at, what action did I take, and what reward did I get at that state action pair. And you're going to collect that data, you're going to get that trajectory, and then given that trajectory, we can then go ahead and compute the true returns that we got. Basically, what is the future expected rewards? Well, we can compute the future expected rewards because we have the full trajectory of the whole game, so we know exactly what the future entailed. So there was no problem there. The issue with Monte-Carlo, although it's a great idea in practice, is that it's not very efficient because it requires us, in complex games like this one, we'd have to first play an entire game, and once we've played a game, then we update our Q values. Then we play another entire game, and then we update our Q values. Then we play another entire game, then we update our Q values. It's not very efficient, especially in large, complex games that could take a while to play. And so the problem here is that how do we deal with this? Well, temporal difference learning was our solution to that. In temporal difference learning, instead of using the true trajectory data, what if we just use our current estimate? Remember, the trajectory data is used to compute our future expected rewards. Well, that's what the Q values are, right? The Q values is our estimate of what the future rewards are at some state action pair. So instead of getting my estimated future expected rewards from true data, what if I use my current estimate of my future rewards instead? And this is known as bootstrapping, right? To use an estimate to kind of update an estimate. By doing this, instead of having full trajectory data to do this update, we just use our current estimate and do the same thing. And this is known as the TD target, right? The temporal difference target. And as you can see, we no longer need this full trajectory because we can just use our current estimate. And of course, at the beginning, our current estimate's going to be garbage. But as the model updates, we hope that this can continue to improve. And so SARSA was the first method we looked at last time, and it is an on-policy method. Why is it on policy? Because it updates the policy based on the action taken in the next state. And this is on the actual action taken in the next state. What does that mean? Basically, SARSA stands for state, action, reward, state, action. So we're at some state, we take some action, we get some reward. When we took this first action at this first state, we'll end up as a new state, right? New state here. And then we're going to take a new action at that state. And my estimate of the future rewards is going to be based on the next state, next action pair. So it updates a policy based on the action actually taken in the next state following the same policy, right? So our estimate for the Q value is based on the same policy that we're behaving on. So we're going to be seeing this in just a second. We essentially have two policies here. We have a behavior policy, what the agent is using to interact with the environment, right? Basically our Q values. And then we have our target policy, the thing that we're trying to update. And in this case, in case of on policy, the behavior policy and the target policy are exactly the same thing. We're using our behavior policy to update itself. And that's basically it. So nothing crazy going on there. This should be pretty intuitive because we again looked at this last time. On the other hand, Q-learning is an off-policy method. Now, notice the difference here. Instead of taking the A prime, which is the action we actually took at that state, the next state, we're instead going to be using the max of A. So this updates the policy based on the highest valued action regardless of the actual next action taken. So you can imagine, let's say your 4 actions are up, down, left, right. And let's say your behavior policy says at this state, you should take you should go up. Let's say it says go up. That's what the behavior policy says. But we know that our max action could be go right. It could be just go right instead of go up. And that means we're going to be using the max policy rather than the behavior policy. And so this is the main difference between off policy and on policy. Let me quickly fix this. This should be a Q right here. update. There we go. Nice. Let's close you. Perfect. So that's the main discrepancy between our on policy and off policy. In on policy methods, we're using the actual, our estimate is based on the actual action taken at that next date. Where in off policy, we're using, regardless of what action we took at the next state, let's just go ahead and use the max one. And that's the main difference between Q-learning and SARSA. So here's some of the main differences you need to keep in mind between on policy and off policy. So first one, in on policy, like we mentioned, it uses the actual future action A prime, right? We're using the actual future action A prime. But in off policy, we're using the greedy policy is what it's called. Greedy because we're just going to say regardless of what future action we actually took, we're going to use the action that has the maximum Q value instead as our estimate. Now, this obviously assumes that our Q table is already optimal. Like it already knows what the best policy is at all the different, or what the best action is at all the different states. That's obviously not true, but iteratively it does work out that way. So we hope it'll end up learning that. Okay. And then the second thing is it learns, on policy again, learns the same behavior policy. So the behavior policy and the target policy, the thing we want to update, are the same thing. So they just kind of learns itself. So it's no big deal. And off policy, it learns a different greedy policy independent of the behavior policy. So this greedy policy, or the target policy, the thing we're updating, is different from the behavior policy that we're actually using to move the agent around in this game, how the agent makes its decisions. Now, of course, on policy will be much more stable. It's more stable because it matches the behavior and the target policy, right? The thing we're using to move around in the game and the thing we're updating are the same thing. So of course this is going to be more stable. On the other hand, off policy, because they're different, right? It's going to be more unstable way of learning. But here's the main takeaway that you should think about when doing on versus off policy, and this is sample efficiency. So it's not really something we've talked about yet, but think about it this way. If my behavior policy and my target policy are the same thing, and I collect a bunch of data about kind of how our agent is interacting with this environment, well, if I go ahead and update my behavior policy, well, that also updates, or if I update my target policy, well, that'll also go ahead and update the behavior policy, which means my policy is completely changed, both my target and the behavior, because they're the same thing. It's the same policy. This means all of that previous data I've just collected from my environment is now garbage. It no longer has any meaning in my new policy space, right? We've updated both the target and the behavior policy because they're the same thing. So all the previous decisions, all the previous state action pairs and rewards and how the agent interacted with the environment, none of that matters anymore because it's no longer defined by my new set of policies. On the other hand, in off policy, because the target and behavior is always different, we can actually reuse data even when we update. Because think about it this way. My target policy is always the greedy policy. I'm always updating based on the max, my greedy policy. What's the best action that I can take regardless of the action that I ended up actually taking? Well, even if we go ahead and update our target policy, which is what we do, then my behavior policy just kind of continues to do what it's doing. It'll just kind of keep running in the background and we'll keep using it. But in the end, it's the target policy is always a greedy policy. So because these two policies are different from each other, because our target policy and the behavior policy are different from each other, then updating one doesn't really mean that all of that previous history of stuff that we've collected, all the data that we've collected, is unusable anymore. We can continue to use it because it's totally fine, because we have two different things, two different policies kind of happening concurrently. This won't matter so much today, but this will matter more when we go to train neural networks, right? When you do deep Q learning and stuff like that. So we'll get to that in the future. But for today, let's go ahead and implement Q learning. It's going to be relatively straightforward and almost identical to the SARSA code, just with a couple of small differences, namely using the max method. So let's go ahead and do that. So as always, we're going to need numpy as np, import gymnasium as gym. And we're going to need our epsilon greedy. So if you remember, we want to, some proportion of the time, we want to take some random actions so we can so we can explore the environment, and some proportion of the time we want to follow the policy. What does the policy say we should do in this specific state? So we're going to write that. This code is identical, epsilon greedy, identical to before. We have our Q table. We have what state are we in, what is our epsilon, so what proportion, and we'll see that in a second, and then our environment. And so we're going to do if np.random.rand is less than epsilon, which we'll set to, I believe, 0.1. So that means 10% of the time we're going to be selecting a random action, and then 90% of the time we'll be following our policy. And of course you can pick any proportion you want or write a scheduler or something like that, but for now this is fine. Action space dot sample, right? Go ahead and just sample a random action if we're less than epsilon, less than 10%. Else we're going to return np.argmax, right? What is the best action that I can take at the specific state based on our Q table? So there you go, that's our standard epsilon greedy setup. And so now we can do Q learning. And Q learning, we need the environment, num episodes, how many games do we want to play? So let's say 25,000. We have alpha is 0.1. This alpha is going to be our learning rate. If you again remember, we have our update formula. Let's go back here. Here we go. It's this alpha t right here. So our Q values are Q value plus basically an update constant, learning rate constant, and then TD target, which is either, in our case, will be the Q learning TD target with the max minus our current estimate, right? There we go. So let's just go ahead and do that. That's our learning rate alpha. Of course, you can write a learning rate scheduler there as well. We have a gamma, which is going to be our decay, right? Our decay over the number of states. How much importance do we want to put on current actions versus future actions? And then epsilon is 0.1. So what proportion of time do we want to select a random action for the exploration of our environment? So np.zeros. Of course, our Q values, we'll just initialize them as zeros because we don't know anything yet. So observation space.n and then env.action space.n. And we can now go ahead and start writing our update. So this code, again, this code is 95% identical to the SARSA code from before. Just we need to change our TD target. So our state are going to be for episode in range num episodes, right? So for every single game we want to play, we're going to first go ahead, sample a state, env.reset, so that's us starting the game, and then we're going to select an action to take at the state. So action is going to be based on the epsilon greedy, and we're going to give it our current Q table, the state, epsilon, and the environment. Right, so we've started a game at a state, and we've selected an action using our epsilon greedy selection process, right? So either, again, select the best action based on the Q table, or select a random action if we want to explore a little bit. Now that we have that, let's do done equals false, and we're going to do while not done, so let's just play the game. First, we're going to go ahead and take a step in this environment. So next state, reward, done, and then stuff we don't really care about right now is env.step action. Go ahead and take a step inside this environment with this action. And that'll give us, we took an action at this state. That means we're going to get a reward for taking that action. And we also figure out what is the next state that we end up in. So there we go. And then at this next state, we're going to find our next action. So that's going to be next action is going to be equal to epsilon greedy Q, next state, epsilon, and env. So this is the action I've selected to take at the next state, right? There we go. Now, here's the key idea. We don't care about the next action when doing our update. So Q state action is going to be equal to, let's review here again, in our onPolicy method from before, we cared about what was A2, right? A2 was the next action that we actually took. In that case, we would actually use this next action here. But in our offPolicy method, which we're doing now, we just want the max action instead. So that's what we're going to be doing. So our Q state action is going to be, again, Q state action plus our learning rate times our reward, and this is going to be the TD target, plus gamma times np dot max, right? Because we wanted the max Q value at the next state. So what I've done here is my TD target is my reward plus my gamma discount factor times the which action it has the maximum Q value in that next state. So we go ahead and take the max. It gives us the max Q value. And now that we've done that, we're going to do minus Q state action just like before. And we are now good to go. Yeah. So that's the main discrepancy. And I'll show you the SARSA code in just a second, just so we can see the difference between the two. But now we can go ahead and do state action is equal to next state next action, just like that. And we can return Q. And that is essentially our Q value update. Instead of doing our SARSA update, we did our Q value update. So as a quick recap, right, let me just find the SARSA update formula. It'll be identical. It'll look like this. If we had done SARSA, let's go ahead and, oh, I copied too much. Sorry about that. Let's just grab U. There we go. And we can delete U. Here we go. So this would have been SARSA, where we're using the Q value of the next state, next action pair. That is our estimate that we're using. In Q learning, we don't care about what the next action was. We just want the Q value of whatever was max. So this is what makes it off policy, because we're updating using an estimate from a policy, the greedy policy, which is different from the actual policy we're using to update or interact with the environment. Because when we're interacting with the environment, this is the actual estimate, right? This is the actual next action we took. But in this case, we're updating the greedy policy, which is not based on the next action we took. So it's different, right? The greedy policy is different from our kind of this original policy right here. And that's the only difference between SARSA and Q learning. That's essentially it. And so now that we have all that, we can go ahead and wrap this up. I'll just copy the rest of this because all the code is identical to the SARSA. So we're going to go ahead, play a game. Looks like, oh, right, of course it won't be SARSA. This is going to be our Q learning. And this will be, let me fix this real quick. We need, yes, so this is not going to be like that. Let me just go ahead and copy the correct thing so it's all good to go. There we go. And this Q should be out here. There we go. So it's going to go ahead and play all the games, generate some policy. There we go. And then we can run our test policy function from before as well. And it shows that we have a 74% success rate with this learned policy. And so again, the main takeaway is this. Q learning is an off policy method. SARSA is an on policy method. And the reason SARSA works well is because it's very stable, because we essentially have two policies going on. The policy that the model is using to, or the agent is using to interact with the environment. And then we have the policy that we're actually updating. And in on policy, these are both the same things, but in off policy, they are different from each other. We have the one policy that the agent is using to interact with the environment, but then we update only the greedy policy because we're only using the max as our estimates. And so this is the main difference. There are some benefits in sample efficiency and inefficiency that we'll see when we get into deep Q learning, especially in the future. But for now, I'm going to call it here. So I will see y'all in the next one, where we start implementing some interpolations between Monte-Carlo and Q learning, namely TDN and TD lambda. So I'll see you in that one.